ladies and gentlemen, and welcome to this afternoon's session on biomimicry. My name is Rob Kerr. I'm the Corporate Manager of Community Energy for the City of Guelph. I'm not the Mayor of Guelph, as the agenda might suggest. Mayor Karen Farbridge sends her greetings today through me, and it's a pleasure to be here. Expect a very exciting presentation. Michael Pawlyn will describe 3 transformations needed to shift from the industrial to the ecological age. Radically increasing resource efficiency, shifting resource use from a wasteful linear model to an efficient closed-loop model, and moving from a fossil fuel economy to a solar economy. And Michael will illustrate how biomimicry, an emerging discipline that offers architectural solutions inspired by nature, can address important challenges of the future. A little bit about our speaker today. Michael Pawlyn set up Exploration in 2007 to focus on biomimicry, an emerging discipline offering innovative architectural solutions inspired by nature. From 1997 to 2007, he worked with Grimshaw Architects and was part of the core team of architects that designed the Eden project. He was also responsible for leading the design of the biomes and a number of other projects that explored innovative approaches to sustainable design. Michael has lectured widely on the subject of sustainable design in the UK and abroad, and in May 2005 delivered a talk at the Royal Society of Arts with Ray Anderson, the CEO of Interface. In 2006, he was appointed to represent Grimshaw as a founding member of the UK Green Building Council, and in 2007 was elected as a committee member of The Edge, a think tank dedicated to addressing important political, social, and professional issues. Michael has taught a number of courses about biomimicry at Schumacher College with some of the world's leading figures in the field, and is currently working on the ambitious Sahara Forest Project, as well as a book titled Biomimicry in Architecture. Ladies and gentlemen, please welcome our keynote speaker, Michael Pawlyn.
Thank you. Well, thank you very much for that introduction, and thank you for inviting me to speak here today. I'm going to start off with a little sort of provocation, really, because I think most people now accept the case for sustainable design. But I also sense there are 2 common feelings. One is a question of, okay, so what next? And the other is a certain sense of sort of dissatisfaction with the term sustainable. And I think Amory Lovins captures this quite nicely when he says, you know, if you were to ask one of your best friends, how's your relationship with your partner? And they were to say, well, it's sustainable. You'd probably say, oh, I'm so sorry to hear that. And the word sustainable does seem to imply something that's just about good enough, just about bearable. And what I'm going to talk about today is a source of ideas that I think will allow us to go beyond standard approaches to sustainable design and to really explore what I think is next, which is restorative design. And this is biomimicry, which uses nature as a source of inspiration for new solutions. And when you think about it, nature is a pretty good source. It's had an R&D period of about 3.6 billion years. And to make things even better, all the faulty products have been withdrawn from the marketplace. So it seems to me it makes sense to make use of that. And I'll just describe a couple of quick examples. That bizarre image you're looking at there, that is a photograph of spinneret glands on the abdomen of a spider. And those produce 6 different types of silk, which the spider spins together into a fiber tougher than any fiber that humans have made. The closest we've come is with a fiber called aramid fiber, or Kevlar by another name, which is what we make bulletproof vests out of, and so on. And it's interesting if you compare the way these things are made, because to make aramid fiber, what you have to do is you take petroleum and you boil it in sulfuric acid at about 750 degrees centigrade. And then, following the principle that if brute force doesn't work, well, you obviously haven't used enough, you then pile on extremes of pressure to get all the molecules into place. And out of that, you get your fiber. You also get a huge amount of toxic waste. So extremes of energy, extremes of temperature and pressure, and loads of pollution, and all that to do the same as a spider does at room temperature with raw materials of dead flies and water. It does suggest we've still got a little bit to learn. And here's another one which I quite like. This is the bark beetle, which can detect a forest fire at roughly 80 kilometers. And if you compare that with man-made fire detectors, our fire detectors have a range of about 8 meters. So this has 10,000 times the range. And what's more, it doesn't need a continuous connection back to a power station burning fossil fuels. You might wonder why on earth would a beetle fly towards a fire? Well, it actually flies to where the fire has just passed through, and it lays its eggs in the freshly burnt wood. And there is a popular science explanation for this, which is that when it gets to where the fire has just passed through, all its mates are there. It can have unlimited sex with no predators around, and you don't get much better than that in the beetle world. But the more important point is that it's an example of an incredibly specific adaptation that this creature has evolved into, because it's treated that niche as an opportunity. And it gives a sense of what biomimicry can really deliver. Because if we could learn to make things and do things the way nature does, then there's a real chance that we could make really radical increases in resource efficiency, achieving factor 10 or maybe even factor 100 savings in resource use. Achieving the same result, but with a fraction of the resource input. And when I talk about biomimicry, I often divide it into these 3 big shifts, which I think we need to embark on over the next few decades. And the first of those, which is the one I just mentioned, is radical increases in resource efficiency. The next one is the idea of shifting from a linear, wasteful and polluting way of using resources to a completely closed loop model. And then the third one, possibly the most challenging of those, is the idea of shifting from a fossil fuel economy to a solar economy. And for all 3 of those interlinked journeys, I think biomimicry has a hell of a lot of the solutions that we need. So I'm going to talk about each of these and illustrate this with projects. And let's start with the first one, radical increases in resource efficiency. And this was something that we were very interested in when we were working on the Eden project. The Eden project is a large botanical visitor attraction in the west of England, and I believe it's one of the largest greenhouses in the world. And we had a pretty tough challenge, really, when we were working on this, because the site that we were designing this for was still being quarried. It was a china clay pit, and it was moving around because it was still being quarried, and we couldn't wait for that quarrying to finish because the design program was tight. So we had to come up with an idea that would work regardless of those final ground levels. And it was really ideas from biology that helped us address all of these challenges. So looking at soap bubbles is what led to the solution that would deal with this difficult terrain. We conceived of the building as being like a string of bubbles, and the diameter of those could be varied to provide the right growing height in the different parts of the building. And then what we called the necklace line that joined those together, that could be varied to suit the topography. We had a rough idea of how the site was going to end up. And the great thing about this was that it wouldn't matter too much what the final ground level was going to be, because what would happen is that the surface would just carry on until it intersected with the ground. Now, you may just be able to make out there's a little line, a faint red line running around those bubbles. Now, that's where we intersected this bubble model with a 3D terrain model. And what was great about that is that if that ground level changed, then the envelope would continue until it intersected, and the integrity of the architectural idea would remain the same. And then it was studying things like pollen grains and carbon molecules and marine organisms like radiolaria that led us to the most efficient structural solution. There are loads of examples in nature of spherical surfaces having a hexagonal structure. And this was pioneered by a guy called Buckminster Fuller, which I dare say many of you will have heard of. And it's a geodesic structure that uses hexagons and pentagons. The next challenge was to think about how we could maximize the size of those hexagons, because that would save us money, there'd be less steel, and so on. And to do that, we knew that we had to find an alternative to glass, because glass is really quite limited in terms of its unit sizes. It's also pretty heavy. And with safety glass, you're limited to about 10 square meters. And in nature, there are a lot of very efficient structures created using pressurized membranes. So that led on to us exploring this material called ETFE, or ethyl tetrafluoroethylene. It's a high-strength polymer, or a saran wrap with attitude, as the client called it. And the way you use this is you put it together in 3 layers, very thin layers, you weld it around the edge, and then you inflate it. And it's the inflation that gives it its rigidity. And those inflated pillows, as we call them, the biggest ones were about 70 square meters, so much bigger than double glazed units, and also far lighter. These were about 1% of the weight of double glazing. So that was a factor 100 saving, both in terms of resource use and in terms of the embodied energy involved. And what we found is that we got into a kind of positive cycle in which one breakthrough facilitated another. So with such large, lightweight pillows, it meant we had far less steel. With less steel, we were getting more sunlight in, so we didn't need to put as much additional heat in the colder times of the year. And with less overall weight in the superstructure, there were big savings on the substructure. And at the end of the project, I realized that we had a pretty accurate figure for the volume of the air inside this building and also the weight of that superstructure. And it turned out that the weight of that superstructure was actually less than the weight of the air inside the building. And if we were to go through that again with a slightly bigger budget and better building technology, I'm confident that we could take that steel weight down by a factor of another 4. And you know, in nature, there's just so many fantastic examples. There's a whole host of sources that we can look at, from crab shells to grid shells that achieve a maximum effect with a minimum of resources, caterpillar eggs that use local resources in phenomenally efficient ways, lightweight bridges based on plant cells, stadium roofs inspired by water lily leaves. This canopy was based on bird skulls. Bird skulls actually combine the efficiencies of dome technologies with space frame technology. Amazing, you could call it really high technology, just in a humble little magpie, and that exists. And here's the stadium roof I just mentioned. This is in Rome, and it's by a genius engineer called Pierluigi Nervi, who used natural sources of inspiration throughout his career. And by doing that, he actually managed to win a lot of his projects in competition because he outcompeted his competitors by making things lighter and cheaper. And this form of construction, this is based on abalone shells. Now, some of you might be thinking, well, this isn't particularly new. You know, architects have been looking to nature for inspiration for centuries, and that's true. But the point is that now we can do it with much, much better scientific knowledge and far better design tools. So for instance, abalone shell, if you look at it under an electron microscope, you can see the sort of subtleties of the microstructure. So although that is almost entirely the same material as ordinary drawing chalk, just through the interfaces and the use of polymer in those interfaces, it's able to achieve 3,000 times the toughness of chalk. And you could characterize nature by saying that in nature, materials are expensive and design is cheap. And what that means is that nature tends to use materials incredibly efficiently. It just puts them where they need to be, and where there's no material required, it just has a void. So this is a diagram of stresses passing through a bone. And the next image shows, this X-ray image shows the bone filaments. And you can see there's an exact match between where the bony filaments are laid down and where there's a concentration of force. So where you need material, you have material, and where there's no force, you just have a void. So really, all these examples show that there's a world of beauty and efficiency to be explored in nature, using biology as a design tool. And I think these examples show how ideas from nature can lead to radical increases in resource efficiency. If we could achieve the kind of low energy manufacturing that the spider does, and then combine that with extremely efficient structures, then we really could achieve factor 10 and maybe even factor 100 savings in resource use. So turning to the next big challenge now, this is the idea of shifting from a linear way of using resources to a closed loop model. And generally, the way we tend to use resources is that we generally extract them from the ground, we turn them into pretty short life products, and then we dispose of them. And nature works in a completely different way. In nature, the waste from one organism becomes the nutrient for something else in that system. And let's just think for a moment about how ecosystems develop over time. Let's just say you've got a bare patch of ground, maybe exposed by a small landslip. Then what happens is that very quickly the pioneer species, the pioneer plant species mainly, they arrive and they change the environment slightly and they make it possible for the colonizing plants to establish themselves. They in turn change the environment and make it possible for the secondary colonizers to come along, and they create niches for other organisms. And under the soil there's a whole world itself of worms and insects and microorganisms. And that process of ecological succession continues all the way through to a climax ecosystem. And if we were to think about at what stage in that process the maximum level of biodiversity exists, it might be tempting to think that it would be somewhere in the middle of that process, where you've got a lot of competing organisms competing for dominance. But actually, the diversity continues increasing all the way through to the climax ecosystem, because the number of niches is continuing all the time. And that's just one of the ways in which ecosystems manage to achieve very rich and diverse systems. And it's worth comparing the typical characteristics of man-made systems with those of biological systems, because generally ours are simple, disconnected, and monofunctional, whereas in nature they're complex, interconnected, and symbiotic. In man-made systems, they tend to be linear and wasteful. In nature, it's closed loop and zero waste. Ours tend to be resistant to change. Nature's adapted to constant change. We use a lot of long-term toxins. Nature doesn't. Ours tend to be centralized and monocultural, and so on. I won't necessarily go through all these, but I think if we look down the right-hand column, what we see there is a pretty good indicator of how we need to transform our cities, our industries, and our communities. And there are some schemes that have deliberately set out to mimic these kind of systems, and an early version was this one in Denmark. It's called Kalundborg, where they, as a matter of planning policy, they deliberately co-located a number of industries. And so you had a chemical works, you had a power station, and the waste steam from the power station went to the chemical works. The waste ash from the power station went to a plasterboard factory. The waste heat went to the local municipality and to a fish farm. And they did achieve pretty remarkable things here in terms of reducing waste, reducing water usage, and they achieved $10 million a year worth of resource savings. So that's all great, but some of the individual elements are not that sustainable. A fossil fuel power station is not really the stuff of biomimetic dreams. So for me, there's a much more exciting and more recent example, which is called the Cardboard to Caviar project, that was set up in the north of England by a guy called Graham Wiles. And I've got a little animation here, which I'm going to talk through, which explains how it works. So in their area, they had a lot of restaurants, and these were producing a lot of waste cardboard, and they were paid to collect that, and then they shredded that cardboard and they sold it to equestrian centres as horse bedding. When that was soiled, they were paid again to collect it. They put it into wormery composting systems, which produced a lot of worms, which they fed to Siberian sturgeon, which produced caviar, which they sold back to the restaurants. Now, what's nice about this is that it's turned a linear wasteful system into a closed loop system, and it's created far more value along the way. And I'm going to go into this one in a bit more detail, because the fuller story is in many ways more interesting, particularly the way that it evolved over time. Because when it started out, it was just the first part of that. Graham Wiles was involving people with disabilities in a recycling initiative, collecting cardboard, shredding it, and selling it to the equestrian centre. Then the horsey people said, okay, well, what do we do with this waste? And Graham said, let me have a think, I'll come up with an idea. And the first idea was that he would supply a fishing bait supplier with worms. So he set up the fish farm, he set up the wormery, and he was just about to supply his first lot of worms when the bait supplier backed out of the deal. So Graham Wiles said, all right, Soji, I'm going to cut out the middleman and set up my own fish farm. And this time he decided to work with reforming heroin addicts. A pretty tough bunch of kids, and bear in mind that in the local area, they were spending as much as £100,000 per addict on rehabilitation schemes that were having a roughly 95% failure rate. Now, Graham Wiles has achieved about a 70% success rate at getting the kids off drugs and back into more productive pursuits. So the fish farm was working okay, but they noticed that in winter, the water temperature was too cold, so the fish weren't putting on enough weight. And by this stage, they'd been given quite a bit of former industrial land by a water treatment facility that was adjacent. And so they started growing willow biomass on this. They used the fertilizer from the sewage sludge to remediate this land, and the biomass was used to feed a biomass boiler, which heated the water in winter. The next thing was that they planted up more land, remediated more former industrial land, and they planted it with orchards that provided another cash crop to sell back to the restaurants and local markets. And then it was annoying Graham Wiles that he was having to spend a certain amount of money on fish food to supplement the worms. So he got the kids involved in growing vegetables to make his own fish food. As it turned out, the kids ate nearly all the vegetables, but that was actually good news because prior to that, they were mostly coming to the site each day with a Mars bar and a can of Coke for their lunch. So now they were learning more about healthier lifestyles. And then they reconfigured the water treatment of the fish farm water because it had slightly high levels of nitrates and phosphates. So they created these long tanks that they would grow watercress in that took the excess nutrients out and provided another cash crop. And then something that he's added recently is a maggot farm that uses waste moldy bread. And that approach apparently has none of the smells associated with meat-based maggot culture. And he keeps on going. He's adding more and more things. And the latest thing is a smokery. And this time, and that's to add more value to the fish product. And this time he's working with ex-military people who've come back from conflict zones, often with disabilities, with post-traumatic stress disorder, and so on. So he's been incredibly inventive, looking at waste as an opportunity. And there are a lot of parallels here with the model that I described of ecosystems. Because every time that he's noticed that he's got an underutilized resource, he hasn't treated that as a problem. He's treated that as an opportunity to add something else to the system to create more value. And I know it's a quirky example, but I do think the implications of this are quite radical, because we could apply the same thinking to our cities, looking at the whole metabolism of our cities, looking at all those waste streams, those linear flows of resources, and use ecosystems thinking to transform those big problems into really big revenue-generating opportunities. And that's very much what we've been thinking about on the next project that I'm going to talk about. It's called the Mobius project. And here we're trying to bring together a number of different activities all within one building so we can get the benefit of these synergies. And the first thing is that we're proposing to set up a restaurant inside a productive greenhouse, a bit like this one in Amsterdam called De Cas. Then we would have, within this, we'd have a biodigester that would deal with a lot of the biodegradable waste from the local urban area. This is very much an urban building. And we'd be able to transform that into fertilizer and generate quite a lot of energy that we could feed back into the local grid. We would have a water treatment facility based on living machine technology, which uses plants and microorganisms to treat wastewater back into reusable water, as well as separating off the solids to generate energy. The next thing is we had to have a fish farm, obviously, and that would deal with use the vegetable waste from the kitchen as a feed for the fish and supply fish back to the restaurant. Then we also wanted to have a coffee shop in here, and spent coffee grains are actually an ideal substrate for growing mushrooms. So you can see that we're bringing together cycles of food, energy, water, and waste, all within one building, and trying to get these waste cycles to hook up to deliver far more value. And just for fun, we've proposed this for a very congested roundabout in central London, which is a complete eyesore at the moment. And with just a little bit of replanning, we'd be able to transform that into a space that reclaims areas from traffic and creates open space for people. It would reconnect people with food while transforming waste into closed-loop opportunities. And I think this is really quite a fundamental shift in terms of our kind of economic model, because the typical economic model at the moment involves extracting and mobilizing large quantities of resources which flow through our economies and communities very quickly, becoming waste. If we treat ecosystems as our model, then we could create systems that create far more value, that keep those nutrients within these closed loop cycles, and perhaps most importantly, one of the most deplorable forms of waste, I would argue, is actually underutilized human resources. And one of the really great things that Graham Wiles showed in that scheme was that it's possible to reintegrate these marginalized groups, people with disabilities, heroin addicts, people from conflict zones, and reintegrate them in ways that is much more productive and socially sustainable. So moving on now to the third and final challenge, the solar economy. There's been a big debate about nuclear power, obviously because of the unfortunate occurrences in Japan. And for me, I am firmly for nuclear power. I'm in favor of nuclear power. And this is the reactor we should use. It's very safe. It's only a few minutes away. And it's free and estimated to run for another 5 billion years. Now, some people would scoff at the idea of transforming our civilization onto a solar economy. But if you look at the statistics, we actually receive roughly 10,000 times as much energy from the sun every year as we use in energy from all forms. 10,000 to 1. So that suggests to me that our energy problems are not intractable. It's actually a challenge to our ingenuity. And I'm not suggesting it's going to be easy, but that statistic of 10,000 to 1 does at least suggest that it's possible. And I think one of the keys to this is thinking about deserts more imaginatively. It came as a surprise to me when I was reading about North Africa to discover that a lot of the world's deserts were actually vegetated a fairly short time ago. So, for instance, when Julius Caesar arrived in North Africa, what greeted him was a wooded landscape covered with cedar trees and cypress trees. And the Roman writer Pliny marveled at the abundance of fruit and animals in the forests. And Caesar's armies set about just clearing that, turning it into an intensive farm for the Roman Empire. And to give you some sense of the abundance that existed there, just for the opening party of the Colosseum in Rome, they transported some 5,000 elephants, panthers, and bears from North Africa to Rome. You can say what you like about the Romans, but they certainly knew how to throw a good party. And I think the key thing about that example of North Africa there is that was a very extractive model of land use, and it didn't last long. Within 200 years, the climate had changed locally, and they'd pretty much depleted the fertility of those soils. And there are quite a lot of issues that we wanted to embrace on this project. So not just the idea of shifting from a fossil fuel economy to a solar economy, but very much present in our mind was the rising specter of water shortages and potential conflicts over water. And this example, these are called center pivot irrigation wells, where a well is sunk in the middle and then you have this rotating pivot arm. And in many cases, these are being extracted, the groundwater is being extracted at such a rapid rate that it's starting to turn saline. And when that happens, it's just a matter of time before that land turns sterile. Another thing that we were thinking about very much was peak oil. And I think one of the things that's been most sort of salient about peak oil theory is that it's shown pretty convincingly that it's not that important when a resource runs out. What is more important is when it reaches that peak, because beyond that peak, that's the point at which the economics change really radically, because you've got a declining resource while you've got a steady or increasing supply. So that's the point at which things politically and economically could change very dramatically. And I sometimes find it quite funny when I hear people arguing really vociferously about whether peak oil's already happened or whether it's in 10 years or 20 years or so on, because if you change the time axis, I think it does rather end the argument. Because the difference between those two peaks, that's the difference between the most optimistic and the most pessimistic predictions of when peak oil is likely to happen. And that descent curve that you're looking at there, what that represents is either the most dramatic period of behavioral change and innovation we've ever seen, or it's something a whole lot less palatable. Personally, I hope we decide on the innovation route. And some people have applied peak oil theories to other resources. Here's another one that's looking quite worrying. This is what's happened to phosphate. And this analysis suggests that peak phosphate's already occurred. And the reason that's quite problematic is because we use vast quantities of phosphate in our industrialized agricultural systems. So if we start running out of that, there's a very real chance we could start running out of food. So you can see that there are a lot of issues there that we're trying to address. And again, this comes back to that list of ecosystem characteristics, because one of the differences between man-made systems and natural systems is that we tend to maximize one goal at the exclusion of everything else, whereas in nature, systems tend to evolve to optimize the whole system. So that's what we wanted to do here, whole system optimization. And next, I'm going to show a little animation of photosynthetic activity around the world. And this is over a period of years. And what you can see is that the edges of the deserts move back and forth quite a bit over the course of each year. And what that suggests is that at those edge conditions, it should be possible to make an intervention that could halt or even reverse desertification in certain areas. So if you're working in pretty extreme environments, then if you're a biomimic, you often spend a lot of time looking at organisms that have already adapted to that. And this is one of my big heroes. It's the Namibian fog basking beetle, perhaps starting to get slightly smug about its media profile now, but well deserved in my opinion, because this creature has evolved a way of harvesting its own fresh water in a desert. And the way it does that is that it comes out of its hiding place at night. It crawls to the top of a sand dune, and because it's matte black and very lightweight, it's able to radiate heat out to the night sky and become slightly cooler than its surroundings. So that when the moist breeze blows in off the sea, you get these droplets of water forming on the beetle's shell. Just before the sun comes up, it tips its shell up, the water runs down to its mouth, has a good drink, goes off and hides for the rest of the day. I think it's fair to say it's not a great quality of life, but it's a clever trick, and that's good enough for me. And the ingenuity, if you could call it that, goes even further. Because if you look at the beetle's shell, on the back of its shell, there are a whole series of little bumps. And now those bumps are hydrophilic. They attract water. And between them, there's a waxy finish which repels water. And the effect of that is that as the droplets form on those bumps, they stay in very tight spherical form, which means they're much more mobile than they would be if it was just a film of water over the whole beetle's shell. So even when there's only a small amount of moisture in the air, it's still able to harvest that very efficiently and channel it down to its mouth. So it's an example of a phenomenal adaptation to a really resource-constrained environment. And in that sense, I think it gives a good indication of what biomimicry offers, because more and more over the coming decades, we're going to be facing serious resource constraints. So on this project, we've been working with a guy called Charlie Payton, who invented the seawater greenhouse, which is also inspired by that beetle. And this is a greenhouse for arid coastal regions. And the way that it works is that on the seaward side, you have this whole wall of evaporator grills. And you trickle seawater over those so that as the wind blows through it, it picks up a lot of moisture and is cooled in the process. So inside, it creates a cool, humid growing environment, which is a much better environment for crops in arid regions. And then at the back of the greenhouse, there are condensers which operate very similar to the beetle's shell, just passive condensers. They're just thin-walled polythene tubes, which are like a whole series of beetle shells. And then a lot of that humidity condenses out as fresh water. So it's turning seawater into fresh water just using the sun and the wind and a tiny amount of pumping energy. And one of the remarkable things about the first one that was built was that it was producing slightly more water than it needed for the plants inside. The plants use far less water because it's humid inside, so they transpire less. And this was actually producing a surplus, and they weren't too sure what to do with that because they were nowhere near a town, so they just started spreading it on the land around. And the combination of that and the elevated humidity had quite a dramatic effect on the landscape. This photograph was taken on completion day, and 1 year later, it looked like that. So it's like a green ink blot spreading out from the building, turning barren land back into biologically productive land. And I would argue that in that sense, it's going beyond sustainable design to achieve restorative design. So we wanted to really scale this up. And we wanted to apply other biomimicry ideas to this so that we could get the maximum benefit from it. And when we think about nature, I would guess that we all often think about nature as being all about competition. And certainly competition is important, but the consensus amongst biologists now is that it's nowhere near as important as we once thought. And in mature ecosystems, you're just as likely to find really striking examples of symbiotic relationships in which organisms have evolved to hook up for mutual benefits. So an important biomimicry principle is to look for symbiotic ways of bringing technologies together. And we looked around for technologies that could work well with the seawater-cooled greenhouses. And this was the one we settled on, concentrated solar power, which uses mirrors that follow the sun to focus the heat to drive turbines to create electricity. And the kind of synergies that these two technologies have are, firstly, concentrated solar power needs a supply of demineralized fresh water. That's exactly what the greenhouse produces. This CSP also produces a lot of waste heat. We'd be able to make use of all that to evaporate more seawater and create more fresh water. Both technologies work extremely well in hot, sunny deserts. And perhaps the most important synergy is that the shade beneath the mirrors makes it possible to grow a whole range of crops that would not grow in the direct sunlight. So if these mirrors were placed immediately behind the greenhouse where the humidity is coming out, then it would make it possible to extend this idea of revegetation, of restoring areas of desert to productive land. And this is a sketch showing the basic idea that we would create these 3 hedges of greenhouses with concentrated solar power plants at intervals along the way to create these synergies. And then this computer-generated image shows all the main elements of the system. You've got the sea in the top right, connected by a sea pipe, 3 strips of greenhouses with crops growing in them, crops between, and the concentrated solar power plants along the way. So it's a model for how we could create low to zero carbon foodstuffs in some of the most water-stressed parts of the planet, create abundant renewable energy which we can use to supply to cities, and reverse desertification in certain areas. And that's pretty much all inspired by the beetle, and added into that some ideas of ecosystems thinking. Some of you might be wondering what we would do with all the salts. If we're evaporating vast quantities of seawater, then obviously we're going to be left with a lot of salt. And if you're a biomimic, if you're left with underutilized resources, you don't think, how the hell am I going to dispose of this? You think, what can I add to that system to create more value? So we've done a lot of thinking about this, and there are some great opportunities here. Because different things crystallize out at different stages. When you evaporate seawater, the first thing to crystallize out is calcium carbonate. And the image on the left there, here. The image on the left, that's one of the cardboard evaporators of the greenhouse after it's been in use for a time, gradually getting encrusted with calcium carbonate. And after a time, we could take that out and we could use that as a lightweight building block. And if you think about the carbon in that calcium carbonate, that would have come out of the atmosphere into the sea and then locked away in a building product, which is pretty handy. The next one to crystallize out is sodium chloride, and there are loads of industrial applications for this, some of which are fairly malign. We're going to try and avoid those and concentrate on the more benign ones. Perhaps one of the easiest things to do is to actually compress it into building blocks. This is a hotel in Bolivia made out of salt, and one of the house rules is you're not allowed to lick the walls. Quite why you'd want to, I don't know, but anyway. And at the moment, we're just joking that with this salt, we're going to try and satisfy London supermarkets' demand for overpriced and pompously packaged table salt. Some in London might say that demand is insatiable, but we're going to give it a good go. And then the next thing to crystallize out is a compound called magnesium chloride, and that's actually very valuable. One of the things you can use it for is as a drying agent in low-energy cooling systems. So in the very parts of the world where increasingly we're going to need some form of environmentally friendly cooling, here's a way to do it very, very cheaply and benignly. And one time when I was doing some research into peak phosphate, I probably should get out more, I discovered another thing that you can use magnesium chloride for, because it turns out that most of the useful nitrates and phosphates that pass through our body actually leave through our liquid waste, not our solid waste. And if you add magnesium chloride to this, it forms a compound with nearly all those useful nitrates and phosphates, a compound called struvite, which you can use directly as a fertilizer. So, you know, with the right design and the right packaging, we think there's scope for another product for the London supermarkets here, overpriced urine salts. And then after that, you get pretty much every element of the periodic table, including gold and uranium. And I'm not suggesting it's going to lead to this, but it should be possible to extract a lot of useful nutrients from from those salts and get them back into the world's soils, closing that loop that we heard about, started by tyrants like Julius Caesar. And really what we've got here is a whole benign chemistry set to play with, turning that waste into value. And perhaps one of the biggest opportunities is in the Persian Gulf, where the salinity of the seawater is increasing all the time because of desalination plants. Now, we could actually make use of that waste brine, and we could evaporate it out to dry salts, creating more desert restoration and turning that waste stream into value. So transforming a big problem, the ecosystem degradation of the Persian Gulf, into an opportunity. And as we proceed with the detailed design of this project, there are a lot of other examples that we can look at. So for instance, camels' nostrils are a miracle of water recovery and heat recovery engineering. Camels get a bad rap, really. They may be style challenged, but they're a phenomenally well-adapted species. The sand skink, which can swim in the sand without suffering any abrasion, that could be used to develop scratch-free coatings for the mirrors and the solar panels. The fog-basking beetle you've heard about, the thorny devil, that can actually drink with its feet. It's got a network of capillary grooves on its skin, so if it's standing on damp ground, the water tracks up these grooves to its mouth, it licks its lips and looks rather pleased with itself. So all of those can be used to develop the design. And as I think, hopefully you've seen, that project is combining quite a lot of ideas. It's combining the idea of the shift to a solar economy. It's also bringing in ideas of ecosystems thinking so that we can get the maximum value from what we're creating here. And returning to the three big challenges that I mentioned at the beginning, the idea of radical increases in resource efficiency, shifting to closed-loop systems, and shifting from a solar economy, from a fossil fuel economy to a solar economy. Those transformations, they're not just possible, I believe they're absolutely critical. And biomimicry has a lot of the solutions that we're going to need. We're still in the early stages of this revolution, but I firmly believe that in this transition from the industrial age to the ecological age of mankind, it's going to be biomimicry that provides a lot of the solutions we need. For pretty much every challenge we face, whether it's manufacturing benign materials, creating energy, finding clean water, there'll be solutions that exist in nature which have already solved those problems and have been refined over this long and ruthless process of evolution. And perhaps more than anything, what biomimicry offers is a really positive way to talk about sustainable design. All too often, talk about the environment uses very negative language like cutting, reducing, and eliminating. But with biomimicry, you get into a much more positive vocabulary about abundance and synergies and optimizing. And I do think this is an important point. Antoine de Saint-Exupéry once said, if you want to build a flotilla of ships, you don't sit around talking about carpentry. No, you need to set people's souls ablaze with visions of exploring distant shores. And that's what we need to do. So let's be positive, and let's make progress with what could be the most exciting period of innovation we've ever seen. Thank you. Okay, sure.
Thank you, Michael, for a fascinating and inspirational talk. We have a few minutes, 20 minutes actually, more than a few, for any questions that you might have. There's a couple of microphones, I believe, in the aisleways. Sir?
Hello, that was a terrific talk. Appreciate it. I noticed, and I don't think it's an accident, you didn't talk about oil from algae, biofuels. Is that because you think it's like might be just a stopgap measure and we should really embrace the solar, or is it just a broad topic you didn't want to bring it up?
Great question, thank you. We are very much looking at biofuels, and at the moment the economic case for it is pretty difficult to get it to stack up. But I think there is a place for it in certain applications, and we very much see it as fitting into this kind of ecosystem of different activities that we're creating. So those two main technologies, those are really just the foundation technologies for a whole web that would include biofuels from algae. And interestingly, one of the things that could make a really positive difference to the economics of algae production is if we were to use the cellulose from algae. Now, cellulose is just a waste product from algae, and is actually pretty easy to extract. And we're very close to the point where we could use rapid manufacturing, so using computer-aided manufacturing, and actually use natural polymers to make things out of. And cellulose is an ideal candidate because the polymers actually self-organize into polymer chains. And all we need to do is to create a sort of printer nozzle similar to the spider spinnerets, and then we can actually print with cellulose. And we're very close to that. That's not pie in the sky stuff. So I think that could help make the case for algae.
Okay, we have a question here.
Good afternoon. Thank you for your talk. I very much enjoyed it. Question for you. I enjoyed I agree with your comment on solar and solar being really the way to go. Today there's a lot of talk, of course, a lot of development on solar, particularly with the panels. But the panels are still only running maybe 20–25% efficient. Have you seen any biomimicry, any examples in nature that would help the collection of the solar power to be more effective as far as than later on, of course, conversion to electricity?
Yeah, sure. There is quite a bit of work going on in this field, trying to get closer to the mechanisms of photosynthesis, which is significantly more efficient than the processes in a photovoltaic panel. There is some interesting stuff involving focusing lenses. I don't know if that's inspired by biomimicry, but there are some good examples in nature of focusing devices. The solar systems that we're using are actually much more simple than photovoltaic panels. We're just using mirrors, which has some advantages in that it doesn't use any rare earth metals and so on. But I think there is actually quite a bit of research work involving biomimicry. I don't know the details. It gets pretty sort of heavy on the science side of things, bit heavy for an architect like me.
Just a general interest question. You talk about biomimicry of beetles and crabs and lizards and all that sort of stuff. Is there any work being done to mimic our system? Like, are we taking anything from human biology and building things based on that? Do we have anything unique about us that's useful?
I think you may have stumped me there. Well, I mean, we're not actually that original as a species. I think we share about 98% of our DNA with primates. So there are certainly a lot of things that biomimics talk about that are common to, say, all mammals. So, you know, for instance, at the moment, we're working on a biomimetic office project where we're trying to use the concrete floor slabs to give greater thermal benefits in terms of passive thermal control. And one of the ways that you can do that is by maximizing the surface area, by creating a richly articulated surface, very similar to our lungs. Apparently, the surface area of a human lung is roughly equivalent to a tennis court. And by doing that in our office building example, we're able to mobilize much more of that mass and achieve greater thermal control.
Yeah, one of the observations that has come up in some of the other sessions has been about the customer wanting something. And so can you talk a little bit about where the customer or the consumer or the person fits into this as sort of the driver for wanting this, and not just it's a great idea, but do I really want this?
Sure. Just stay there a second, because I just want to check what you mean by customer. Do you mean the general public, or do you mean clients that would commission a building?
Take this on. So one of the things in all this innovation, Bill Baxton from Microsoft this morning said, you can get a great gadget or whatever. We have too many gadgets. So what is the motivation that people are going to get into this, going to invest in this, and so on? So it's really about the willingness of the customer, consumer, buyer, whatever, to get into this.
Okay, I can think of a number of ways of answering this. I mean, in terms of why they'd be interested, let's take the example of some of the North African or Middle Eastern countries. Now, some of those have got phenomenal solar resources, and there's actually a pretty strong case for arguing that we'd have much greater international stability if we pursue a solar economy rather than a fossil fuel economy, because countries in North Africa there'd be a very strong vested interest in them becoming reliable suppliers of energy to the rest of Europe. And one of the problems with solar energy, which becomes a big benefit, is that it's very difficult to store it for longer than about a day. You can use molten salts to store it for short term and so on, but it's pretty difficult to store it for longer than that. Which means that if there was a high voltage DC supergrid connecting up all the countries of Europe with North Africa, then there'd be very little incentive for a country like, I don't know, say Libya, to switch off power to Europe, because it would just give their neighboring countries the opportunity to charge slightly more. They'd just be shooting themselves in the foot. In terms of Middle Eastern countries, a lot of the countries in the Middle East are very interested in our scheme, because they're now putting together, in a bit of a rush actually, food security plans. Saudi Arabia was until recently a very big producer of grain, and all that was based on an aquifer, which they've now realized is pretty much depleted. So grain production this year, I think, was 25% of what it was 5 years ago, and within 5 years it'll be down to virtually zero. So the other countries that depend on Saudi Arabia, like Qatar and Kuwait and Bahrain and so on, they're putting together food security plans that look for how they can produce more food within their national borders. And another interest is that there are already a lot of people pursuing concentrated solar power. And some of them are interested in synergies, others are still of the mindset of maximizing one output. Now, if they're really dogged about that, then we're not interested in them. But for the ones that are a bit more open, we can offer very big benefits, because we can make their system more productive, more efficient, and we can produce a lot of secondary benefits to the local community. So some of the critics of concentrated solar power in North Africa, say, have said this looks like a land grab, where you're grabbing our energy and you're going to take it to Northern Europe. And there's some good grounds for that. But if we were to partner up with those concentrated solar power companies, we'd be able to provide big benefits for local communities in creating more sustainable agriculture and producing food for their own uses. This is turning into a rather long-winded question. A long-winded answer, but unless there's someone else who wants to ask a question, I'll carry on, because there's another angle to this, which is that in architecture, innovation has proceeded rather slowly. And I think one of the problems is that architects tend to be reactive. We wait for a customer, a client, to say, I want this, and then we do our best to deliver it. Now, the problem with that is often those clients don't come along. Sometimes they do come along, and they'll say, yes, I want a really sustainable building. And then it turns out that they may have already made some of the bad decisions, like choosing the wrong site, setting the wrong brief, appointing a suboptimal team, and so on. And so at Exploration, my company, we wanted to try a different model where we work in a way that's more similar to, say, innovative product designers, where you have a highly idealized idea of the product, you develop it up to a certain point without any compromises, and then you find the client for it. It's much more difficult, but it is working. There's an amusing little anecdote I can tell you, which is that about a year ago, we were concerned that we weren't getting this idea in front of the right people. We'd had a lot of publicity. We've been very lucky. We had an article in the Guardian in the UK and on Tree Hugger, which went all over the world, appearing on blogs and so on. But we didn't get that call from the philanthropic tycoon saying, I want one of these. So we decided that we needed to do something about this. We needed to get it in front of other people, the right kind of people. And I've partnered with this organization in Norway, this environmental NGO, and they heard that the King of Jordan was visiting Norway on a state visit. They managed to get a short meeting with him, and they presented the project to him. And by good fortune, he had with him one of his ministers whose genuine job title was the Minister for Mega Projects. And they both loved it, and they've now commissioned us to do a feasibility study in Jordan. Next question. Sorry, I've taken your job.
I was just wondering if you could briefly speak to how this bridging of biology and design has altered the perspectives and disciplines that sit around your design table, and how you deal with that, if it has.
Yeah, well, good question. And Janine Benyus, as you may well know, she puts this quite nicely when she says that there's scope for a much more creative role for the ecologist in design. In typical building projects, the ecologist just does the environmental impact assessment, usually at quite a late stage. So basically they're brought on to do the body count once the design has been completed. And if you can bring the ecologist in at the very early stages, or the biologist, then there's scope for a much more productive collaboration. So on this project I mentioned, the Biomimetic Office project, at the first meeting we have a biomimicry professor who's going to be there. A small team, there's just 5 of us, and he is one of them. And I do think that designers and architects particularly need to get better at collaborating. And for some reason, at least in Europe, architects have tended to gravitate more towards the sort of artistic end of the collaboration spectrum. And sure, there's some interesting collaborations to be had there, but sometimes I get the sense that architects have a kind of art envy, and that's why they're doing it. I think, given the challenges that we're facing, artists can play a very important role in helping communicate messages about the environment and climate change and so on. And scientists, I think, can play a really important role in the design team. There are so many brilliant scientists working on things just in the laboratories who I think would probably be delighted if they could team up and actually see some of these ideas realized and make a real difference.
We have just a few minutes left. Are there any more questions? There's one.
It's me again. You've focused quite a bit on new projects and new designs, but is there much leg in retrofitting? You know, the whole world is 99% existing and 1% pushing ahead. How could this be applied to retrofits that actually might make a difference?
Yeah, retrofitting absolutely is really important. And it can be challenging doing a retrofit for obvious reasons, because so much of the stuff is already there and you can't change it. And that is quite difficult because biomimicry is really based on rethinking things from first principles. However, I do think, particularly in retrofitting cities, there are a lot of very important lessons that we can apply from ecosystems thinking that I mentioned there, you know, the idea of treating waste as opportunities. I think that there is a huge potential in retrofitting cities, particularly actually if we think about a changing emphasis on transport. If you achieve a shift from private cars towards more compact forms of transport like buses, trains, cycling and pedestrians, you can actually free up a lot of urban land, very valuable land, which you can use for other purposes. You can actually use for building developments to create slightly more compact cities, which then make it possible to get around with less mechanized transport. And you can also incorporate a lot more productive planting and urban agriculture. So I do think there's potential in retrofitting, but it would use slightly different aspects of biomimicry to do it.
No more questions? Last call. Before we come to a close, just a reminder that there's another round of sessions in the various theaters, concluding with closing remarks for today's session and the conference as a whole in this theater. I'll also let you know that today's session presentation by Michael was taped and will be available on the OCE website in a couple of weeks. So with that, I would like to ask you, and thank you for coming, and ask you to join me in thanking again. Great presentation from Michael Pawlyn.
Thank you.
Thank you.
Thank you.